Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this thermal analysis of cooking pan. In this pan, we have two material. One is pan, another one is handle. Pan is made up of cast iron. Here you can see this is the material property for cast iron. And handle is made up of plastic because heat should not affect our hand. So that because of that, we have made the handle in plastic. And so inside the pan there is a food convection. Here the heat flux is coming from the stove or gas, and out other side the air convection. So heat loss due to the air, here heat loss due to food. So we'll see the material property. Handle made up of plastic. Thermal conductivity of the plastic is 0.23 watt per meter Kelvin, and specific heat and density. Similarly for cast iron, thermal conductivity of the cast iron is 46, specific heat is 510 joule per kg Kelvin, and density. In boundary condition, 31,500 watt per meter square Kelvin heat flux is coming from the gas at the bottom surface of the pan. And food convection, here the food is there, so the convection property, the heat transfer coefficient is 150 and temperature is 22 degrees Celsius. And other surfaces is contacting with air, atmospheric air, of heat transfer coefficient is 10 and temperature is 22 degrees Celsius. Now we'll solve this cooking pan thermal analysis using code aster. First we'll open the code aster. I have kept code aster here, so just open the terminal. So this is the command to open the salome meca file. Just enter it, it will get open. To analyze this model, we need step file. This file I have kept in the below the video. You can download this step file from the below the video. So first we will import this step file in salome meca geometry model. First go to geometry model, go to file, import step. So go to the location, I have kept it in this here, just open it. So this is asking take into account the unit of inches embedded into the file. Ignoring the unit will cause the model dimensions are supposed to be specified in meter. So we need to specify meter. For that we need to apply yes. To check the dimension of the model, just go to inspection, dimension, bounding box. So this is my dimension of my pan. Just close it. Now it has before going into model, first check how many geometry solid volumes are available in this model. For that just go to select this pan 3D, go to new entity. There is an option called explode. So the subshape will show here. I need to see how many solids are there. Just select the solid and apply and close. Now see, we have two solids. So one is this fillet 2. Fillet 2 is nothing but pan, and another one is combined. This is the handle. So in between these we can specify glue contact. Instead of that we can make a partition to what it will make, a merge nodes between this pan and handle. So we can use the second method of partition. So for that, select both, just select both the volumes, go, there is option called operation in that partition. So select both the object here and apply and close. It will do the partition to both the object. Now just go to new entity, explode, solid, apply and close. So this partition having solid 1 and solid 2, this having a shared node between this shared surfaces between these two volumes. What it will make? It will make a connected mesh between the pan and handle. So now this is enough. Now we can create a groups to apply the boundary conditions. Now we'll check the case. So we need this top surface as a foot convection and this bottom surface as a heat flux, and remaining surfaces we need to make it as air convection. So there are two volumes, you just name it the volumes one by one. This is actually a pan and this one is a handle. Now just go to create groups, surface groups. The bottom one is just add it here. This surface number will add here. This one is called heat flux. And this top surface is a foot convection surface. And remaining surfaces all are air convection. Instead of selecting all the surfaces one by one, we can go by select all. It will select all the surfaces. Now what we can do is we can remove these two surfaces from all the surfaces. Press the shift and hold, select both the surface, these two surface, just remove it. This is the remaining surfaces. This is, name it as air convection. Say it okay. Now it is done. Now what we can do, we can go for meshing. Go to mesh module. Now we are in mesh module. Select this partition one. Go to mesh, create mesh. Go to NetGen 1D, 2D, 3D algorithm. Here you can choose it. NetGen 3D simple parameter. Here we can specify 0.005. Save OK, apply and close. Now we need to compute the mesh. Right click, compute. Now meshes got generated. Now we'll check the mesh, how it is looks. Here the mesh is okay, it seems. If you want to make finer mesh, we can make finer mesh. This is enough here. And here we just have a look. Here mesh is not capturing the surfaces. So here what we can do, we can do the submesh here. For that we need to create a surface. Just create group, surface group. Just we'll move it here. These surfaces we need to take it. Just add, apply and close. Now just right click here, edit. Now we'll check any surfaces not selected. All the surfaces are selected. If anything is not selected, we can select one and add it here. Then apply and close. Now right click here. Now go to right click. There is an option called create submesh. So here we need to choose geometry. Choose this group 1. Choose NetGen 1D 2D. Same simple algorithm. Here we need to specify little finer. Previously I have specified here as 0.005, that is a global mesh size. The local mesh size here I am specifying it 0.003. Save OK, apply and close. Now mesh 1, right click it, compute. Now here you can see little finer mesh we have generated here. If you want to make finer also we can make it, but here we don't have an area of interest. So we need not to focus here. Our focus area is here. Here we have mesh that is enough to our analysis. So we can keep this mesh. We can go for analysis. So now we can see here groups also taken into the mesh, heat flux, food convection, air convection, and 2 volume groups, everything. Now we can save this file. Now we will move into aster study. There are different ways we can analyze this thermal analysis using code aster. First thing is we can generate a command file. We can use ASDK to run the file. To generate the command file, and 2 ways we can do is, one is we can use assistant to generate the command file. Another one is one by one we can add it from using a top icons. We can do it. What I'm going to do in this way, I'm going to use this assistant to generate a dummy command file. From that I'm going to edit it. So next 3D, nothing, I'm going to change it. No boundary condition, just something I'm giving. Here, do you want to apply add a stream normal to phase? Yes. This is nothing but a heat flux. So heat flux value we want to enter it here. 31,500. 31,500. Say next. There is no volumetric source. Volume it generation, just say it no. Next, save this file. Pictures, code aster. Here I'm just want to save it as result 1. Save, finish. Now you see we have generated dummy command file. From that we can edit it. First we need to read the mesh. This is enough. Assign the thermic model. So thermic is okay. Now material, we need to define 2 material. Here you can see there are 2 material. One is plastic, another one is cast iron. So go here, first one edit it. Thermal, scroll down, we can get it. Otherwise we can type it as THE. Thermal model will come here. Just go to edit. This one is a thermal conductivity. First we'll define the material of plastic of thermal conductivity 0.23 and volumetric heat source. This is nothing but rho into Cp. So we need to multiply the Cp into density. So just go to calculator. Cp is 1390 into density is 1050. So this is the value we need to enter it. Just copy it. Just go here, paste. Now save OK. Just apply it. Now see, this is the command it will generate at the back. Save OK. And we need to rename this material also. This is a plastic. Say apply. OK. The another material we need to define. Just go to material, define material. That is a cast iron. Cast iron, same, go to thermal. Here there is an option called isotropic heat conduction properties. Here specify the thermal conductivity is 46. Similarly, volumetric heat source, Cp multiplication of density, rho into Cp. So just multiply this using calculator. 510 into 7200. The value is 3672000. 3672000. Just OK. Just apply it. Save OK. While naming any model name, we should not use space. We need to use underscore instead. So now we have defined the material. We need to assign the material to specific model. That is option called mat field. Just go here. There is option called, you see, assign a material. So mesh and model. Here we need to choose, instead of everywhere, go to group of element, edit. First one is pan. Pan is a cast iron. Just say OK. Here choose cast iron. Say OK. The second, similarly we need to add here. go to edit, element, handle, save OK. We need to add it here. This is the plastic, save OK, then apply it. Now you see the group of element pan is a cast iron, material is assigned, handle plastic material is assigned. Now we have assigned the material to the mesh model. Save, apply and OK. Now we have assigned the material. Now we need to define the loading conditions. That means boundary conditions. Here in our case there is no enforced boundary condition, I mean fixed temperature boundary conditions. So heat flux and two convection boundary condition. Just remove this one. Heat flux we have defined. Another one is a convection boundary condition. For that go to exchange, add, edit. So for convection boundary condition we need to define the surface area and heat transfer coefficient and external temperature. So surface area it will take from the element group. First one will define foot convection. So foot convection is nothing but inside surface. Here there is a foot convection, save OK. Surface we have defined. Heat transfer coefficient and external temperature we need to define. Go to here. Heat transfer coefficient is 150, external temperature is 22. Heat transfer coefficient is 150, external temperature is 22. Save OK. Now there is a one more convection boundary condition. Just add it here. Edit, group of element, edit, air convection. See, other the surface. Save OK. Now heat transfer coefficient and external temperature we need to define. For air convection, heat transfer coefficient is 10 because the air having a less heat transfer coefficient. So 10 is and external temperature is 22. So now just go here. Heat transfer coefficient is 10, external temperature is 22. Save OK, then apply. Heat flux we have defined. So this is a heat flux surface. Flun is nothing but the heat flux. So 31500, save OK, then apply it, save OK. Now we have defined three boundary conditions. Now we can solve this. So this is the solver. So it has taken the solver. This is enough. Save OK. Linear solver, linear temperature thermal solver. Now output, it will save the output as a thermal. It will give only the temperature as a primary variable. It will solve and it will give the results. So it will save in the MED format. Now save this file. Now we can run this file. Just go to history view. Click this plus button. Now change this into 5 seconds. If you want to change this into you want to increase memory to solve the case, we can increase. So number of CPU we cannot change it. So here we can change the version also. So I'm just using the 15.6. Now we can run it. In this window is for to view the message file, output message file. Just wait for a while, it will get solved. Now it's reading the command file. If any error comes, it will show in the message file. From that we can rectify the message file. Now you see here the problem is getting solved without any error. It shows diagnostic job is okay. Now we can see the result using paraview. Just go to paraview. Just open it. Pictures, code aster. The result file will check the name of the result file. The name of the result file is result1.output and it is saved in this is the, so result1 is the output file. So actually it's not named with the RMD, so just rename into .rmd. Just rename it. .rmed, then only it will show in the paraview. So now just go here, just go to paraviews, right click and open. Now you see result 1.rmed, just save. Now see the temperature is a variable, it is calculated, just apply it. So this is the pan, we have temperature. So this is the way the heat is transferred from the bottom surface to the top surface. To view in a different color, just click it here. There is an option called this. This way we can check. This is the way heat will get propagated. And another we can go for here, rainbow, blue to red, apply, close. Here we make it 10. So this is the way heat is getting propagating in the pan. So here heat flux is coming, is getting conduction is happening, and convection is also happening. So the maximum temperature is coming around 220 here at the bottom. From that the temperature is less. At the handle you can check around 27 degrees Celsius. So it's like atmospheric temperature. So we cannot feel the temperature, the hot temperature to the handle. That is because of we have used less heat conductive material of plastic. If you want to check the temperature value in a specific location, you can go for this point, hover point, and you can place it here. Here the temperature is 211. Similarly, we can move it and we can check it. Here 213, 212, like this the temperature is varying. At the bottom also we can check, just rotate it. Here 214, 217, somewhere is coming 220. So in that way we have finished thermal analysis of cooking pan. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.